Hello everyone, welcome to DP Tutorials by Donny Jerwa. In this teaching module, we will emphasize and accentuate on a topic which is of the magnetic force on a charged particle which is placed in a uniform magnetic field. Now, when we are talking about this chapter, which is related to magnetic effects of electric current, we know that if I have a wire and if I pass current on this wire, I know that there will be magnetic field lines associated with this wire. So that is the concept of what? Magnetic effects of electric current. We have dealt with Biot-Savart's law. Okay, we have also dealt with Ampere's circuital law for different types of geometrical shape. Now over here, when it is dealing with charges, okay, charges in nature are of two types. We have positive charges and also we have negative charges. If we go into the microscopic phenomena, the protons will be having the protons are those types of particles which are positively charged, and the electrons are those types of charged particles which are what? Which are negatively charged. So these are the types of what? These are the types of charges which we will discuss. Now when we place these types of charges in a uniform magnetic field, say like if you place a proton inside a magnetic field or if you place an electron inside a magnetic field, it will experience magnetic force, and that type of magnetic force is known as what? That type of magnetic force is known as what? Lorentz magnetic force, because it was governed and studied extensively by this Lorentz. Okay, so this picture which I have shown over here is the picture of a Dutch physicist by the name of Hendrik Antoon Hendrik Antoon Lorentz. Hendrik Antoon Lorentz. So he was the particular person who is a theoretical physicist from Dutch, that means from Netherlands. He is a Dutch physicist, and he is a Dutch physicist, and he was born in the year around 1853, and he expired in 1928. Okay? So this was the scientist, and he did a remarkable investigatory relationship between electricity and magnetism. So he is a theoretical physicist. Okay? He is a theoretical physicist. He got a Nobel Prize. Okay, some history about him. He got a Nobel Prize in the year 1902. Okay, in the year 1902, on account of what he explained the Siemens effect. Okay, in account of what he explains the Siemens effect in collaboration with another scientist by the name of Siemens. So that was the contribution about what? About Lorentz. Okay, so from here, when we place this charged particle, if it is a positive charged particle, if it is a negative charged particle, all these charged particles will experience what? Will experience magnetic force. Okay, so over here, let us consider this situation. I have this positive charged particle, and this positive charged particle is moving. When we are talking about motion, that means there should be some kind of phenomena which describes that motion. So it should be what? It should be the velocity. So when we talk about motion, that means the physical quantity which governs motion of a charged body will be what? Will be the velocity. So let us constitute any Cartesian coordinates. Okay, any Cartesian coordinates. So over here, let us choose this x, y, and the z axis, and over here also let us choose x, y, and the z axis. So over here, these are what? These are the directions of the axis. And besides that, I have this positive charge particle which is placed in the xy plane. Okay? I have this positive charge particle which is placed in this xy plane. So over here, let this particle have certain velocity. Let that particle be moving with a certain velocity in the direction of the applied field. So from here, suppose if I have a magnet, okay, I have a magnet from one end and also have a magnet on the other end. Then there will be magnetic field lines, okay, produced by the magnet emanating or coming out from the north pole going to the south pole. So this will be the direction of my B field. So the direction of my magnetic field will be in the direction along the y-axis. So let this be the direction of what? The magnetic field, okay, magnetic field vector along the y-axis, which means that over here there is some angle between the v vector, between the velocity vector and the magnetic field vector. So from here it is determined that the cross product, okay, the cross product of the b vector, okay, the velocity vector and the magnetic field vector will account for what is known as the magnetic force. So from here there will be some magnetic force associated with this positive charge. See, from here this will be the white vector, the white colored vector or the white colored ray represents the velocity vector, and the pink colored ray represents what? Represents the magnetic field vector. From here there is some angle between these vectors. Say if you cross product, when I say cross product, if I look from here, if I say if I take the cross product, that means over here this will be that magnetic Lorentz force. If I take the cross product, that means this v, okay, this velocity vector will be the first vector, and this magnetic field vector is our one, is our second vector. So when you cross product from the first vector to the second vector, that means the third vector will be in a direction which is perpendicular to v as well as b. So from here, making use of this right hand, okay, making use of the right hand, okay, right hand thumb rule for cross product, making use of the right hand thumb rule of the cross product, the direction, if you first of all you align your fingers in the direction of v, okay, you align your fingers, first of all you align your fingers in the direction of what? In the direction of v. So this will be the direction of our one, of our velocity vector. Then I will curl my fingers in the direction of b. Then the moment when I curl the fingers in the direction of b, when I curl the fingers in the direction of b, when I curl my fingers in the direction of b, then these will be my curling fingers. So from here, the thumb, okay, your thumb points in the upward direction. Since the thumb points in the upward direction, so it means that that force, okay, this force will act in the upward direction. So this thumb points in the upward direction, okay, the thumb points in the upward direction, so which means that over here your force will be acting perpendicular to the velocity vector as well as perpendicular to the magnetic field vector. So from here, making use of the right hand thumb rule for cross product of two vectors, velocity and your magnetic field vector, then it is evident that the force in which this charge particle will move, which means that this charge particle will move in this direction, which means that if I have a plus charge over here, that means this plus charge will experience a force and will move in the upward direction, which means that this positive charge will move in the upward direction perpendicular to the direction of one of your magnetic field. So from here, okay, so from here, making use of that analogy, I will represent by this yellow colored vector, and then I will place over here, that means this positive charge particle will move in the direction of this yellow colored vector representing the magnetic force. Okay? Magnetic force. Force is a vector quantity, that is why I put by the vector sign. Similarly over here, the direction of this magnetic force will be what? Will be given, okay, the direction of this magnetic force will be given by this yellow colored vector, and it will act on what? It will act on this direction. So this will be what? This will be your direction of the magnetic force for a positive charge particle. Now, if I consider for a negative charge particle, that means for cases like electrons, okay, if I place this charge particle on the Cartesian coordinates, suppose if I name this as the x, y and the z axis, okay, these are the coordinates, these are the Cartesian coordinates. Now, if I consider this negative charge, that means this like the same case only, I have one end of the magnet over here, one pole of the magnet over there, and another pole of the magnet over there. I know that the direction of the magnetic field lines will always start from north pole to south pole. So this will be my direction of what? My direction of our magnetic field lines. So the direction of our taken magnetic field lines will be along what? Will be along the direction of your y-axis. So magnetic field will be along the y-axis. So from here, let v be the velocity. Okay? Let v be the velocity of this minus charge. Okay? Let v be the velocity of that minus charge or negative charge. So this is the velocity of our negative charge. Then from here also there will be the cross product. The cross product will be in this direction from the first vector to the second vector. Then in order to find the direction, since there will be force, if the charge particle is moving with a certain velocity under the influence of this magnetic field, then what will happen to that charge particle? This charge particle will experience what? Will experience that magnetic force. So this will be the magnitude of that magnetic force. But since force is a vector quantity, you need to find the direction. So making use of this left hand, this is your left hand, making use of left hand thumb rule for cross product of vectors for this negative charge particles. You take your left hand and then first of all you align your left hand in the direction of your B field. So when you align your direction in the direction, or when you align your fingers in the direction of your what? Of your velocity vector, and then you curl your fingers, in the direction of your magnetic field. So your magnetic field will be in this direction. So where will your thumb point? Your thumb will point downwards. So which means in this case, since the thumb is pointing downwards, so at that particular point, that means over here, this will be the direction of what? This will be the direction of a magnetic force for that negatively charged particles, which means that over here, if I have this negatively charged particle, this is my velocity vector, and this is my magnetic field vector, and this is the angle between V and B. These are my Cartesian coordinates, okay, x, y, and the z axis. If this is the positive z, then this will be the negative z, okay, z dash. Okay, over here also the negative z, which is our z dash. Then from here, this will be the direction of my v. Okay, this will be the direction of v, and this will be the direction of b, velocity vector and magnetic field vector. My thumb is pointing in the downward direction, so that will give us the direction of the magnetic force. So which means that this negative charge particle, instead of moving upwards as in the case of positive charge, this negative charge particle will move what? Will move downwards. Okay, this will be what? That will be the force. Okay, that will be the force in which your negative charge particle will experience. Okay, will experience. So from here, making use. Okay, so if you take the negative charge, and when the magnetic field lines are moving along this direction by the help of this magnet, by this help of this source of magnetic field, then this negative charge particle will move downwards, represented by this yellow colored ray. Okay, that yellow colored ray will represent the magnetic force in which this negative charge particle will move downwards. Similarly, moving along the negative z direction. Similarly, over here, this negative charge, okay, it will experience a force, and that force will move downwards, okay, represented by the yellow colored vector. So this will be what? This will be the direction of our magnetic force moving in the downward direction. For the negative charge particle, if the magnetic field is in this direction, then the direction of the magnetic force will be downwards. See, if I have a positive charge, and this is the direction of our magnetic field. See, if I have a positive charge, and this is the direction of my magnetic field, then where will be the direction of the magnetic force? This will be the direction of my magnetic force. So what Lorentz investigated is that, okay, he found out that there's an empirical formula which he established from here. Okay, you consider this charge particle which is placed in uniform magnetic field of magnetic field B bar along the y-axis, and over here let V, okay, be the let V be 1. Let this V be the velocity of the charged particle which is moving along the xy plane. So this charged particle is moving along this xy plane. This is my xy plane. This negative charged particle is also moving along the xy plane. And this direction in which the v vector and the b vector makes, this angle is how much? Making an angle 1, making an angle theta with the magnetic field direction. So when the charge moves through a uniform magnetic field, what did I say? It will experience a magnetic force. And this magnetic force is always perpendicular. See, this magnetic force is always perpendicular to this plane. Okay, if I have a plane, this is my plane containing the v, the velocity vector, and the magnetic field vector. Then the direction in which my magnetic force experience, that means this will be the direction of my magnetic force, and this magnetic force is always perpendicular to this plane, okay, to this plane containing the v and the b vector. Similarly over here also, for that negative, in this case this is for one, this is for the positive charge particle. In this case this is for positive charge particle, and in this case this will be for the negative charge particle. The velocity is acting on this direction, and the magnetic field is acting on this direction. But what happens to our direction of v? The direction of our magnetic field is in the direction of the magnetic force, I mean, it is in this direction, which is perpendicular to this plane containing the two vectors. Okay, so it is perpendicular to one, it is perpendicular to the velocity vector v and the magnetic field vector b bar. Okay, so it is found out, okay, it is found out that the magnitude of this force, okay, the magnitude of that force F is directly proportional to the charge 1, to the charge q, and it is also dependent upon the velocity v. Okay, the charge I can write in this form. Okay, it is dependent upon the charge q of the ion, and then it is also dependent upon the velocity v. Okay, it is also dependent upon the velocity v. It is also dependent upon what? The strength of the magnetic field, and is also dependent upon the sign of the angle between what? Between v and b bar. Okay? V and b bar. So which means that is that this magnetic force is what? That this magnetic force, that means over here F is proportional to Q from the first condition, F is proportional to V, second condition, F is proportional to B, third condition, and F is proportional to the one, to the sign of the angle between the two vectors. Since V and that B are what? Are acting on the same plane, are acting on the same plane. Both, you should always remember that V and B should act on the same here, on the same plane. So such that the force will act in what? Will act in the perpendicular direction. So if you combine those terms, that means over here this will be equal to B, okay, Q, okay, V, and the sign of the angle between them. Okay, the sign of the angle between them. So from here, when we rewrite this equation, okay, we have to write in this form, removing the proportionality sign. We got an equal sign and a constant of proportionality k. Okay, so this is equal to like this, BQV sine of theta. Yes, sine of theta. But in SI unit, okay, in SI unit, the value of k is taken to be equal to 1. Okay, in SI unit, that value of k is taken to be equal to 1. So if you put this equal to 1, which means that Lorentz magnetic force is given by this equation, F equals sign BQV sine of the angle theta. So this equation, I can mark this as equation 1. This equation 1 represents the magnitude of our Lorentz magnetic force. So this is the very important equation. It is important for solving numerical problems. If you know that, if you want to find the magnitude of the magnetic force, knowing the values of B, knowing the values of Q, and knowing the values of V, and also the angle between V and B, you can find out the magnetic force. Okay? So this equation 1 is only expressed only in terms of what? Only in terms of magnitude, which we can say that this is in what? This is in scalar form. Okay? This is in scalar form. But if you want to express this equation 1 in vector form, that means you have to introduce the cross product. Since we have the sign of the angle, I have the sign of the angle. This sign gives me an idea about what? Cross product. Say, if you recall or reiterate from this diagram, it is very obvious that this V, okay, it is very obvious that the velocity vector is in this direction and the magnetic field vector is in this direction. So the magnetic force is in the plane which is perpendicular to V and B. So it is the cross product of V and B, cross product of velocity and magnetic field vector. So from here, this force, okay, this equation 1 can be written in this form: F bar. Okay, the moment we introduce the sign, that means this Q is scalar, so I can take outside. Then I'm left with what? I'm left with V B sine of 1, sine of theta. So this, okay, can be expressed. This can be written in that form. Okay, I'm just rewriting in another form. Then from here, if I introduce the vector notation, okay, V F bar. So over here, this is VB sine of theta. So V, velocity, is the first vector, and magnetic field is the second vector. So it will be 1 V cross B bar. Okay, V cross B bar. So this is our representation of the magnetic of the Lorentz magnetic force in terms of what? In vector form. Okay, this is the representation of magnetic Lorentz force in vector form. So over here, I have been explaining to you that V and B lies. This V and B lies in the same plane. So from here, the cross product of the V vector, okay, the cross product of the V vector and the cross product of the V vector and the B vector is the magnitude of the force F, which is perpendicular to both the V and which is perpendicular to both the B vector. Then the charge. So from here we will study some of the special cases. Okay, some of the special cases. When the charged particle, what happens? Suppose when the charged particle is at rest. When the charged particle is at rest, it means that the velocity is equal to 1. The velocity is equal to 0. So when the velocity is equal to 0, it is obvious that when the charge is not moving, so obviously there will be no magnetic force. So if you look from that particular example, if the charge is stationary, okay, if the charge is stationary, if there is no velocity, so there will be what? The charge itself will not experience any magnetic force. So from here, how will you solve that? Making use of this equation BQV, okay, sine of theta. So from there, if you put V equal to 0, if you put V equal to 0, so this equation itself will reduce to 0, which means that the magnetic force is equal to 0. So which means that if force is 0, if the magnetic force is 0, that means the charge will not experience any motion at all. When the charge is at rest. When I say at rest, it means that the charge is what? The charge is stationary. Okay? The charge is stationary. Then, when the charge is, suppose let us consider when the charge is moving in the same direction, when the charge is moving parallel to the direction of B. Like for instance, okay, when I say moving parallel to the direction of B. So from here, when you look from that diagram, okay, when you look from this diagram, it is very clear that if I have this positive charge particle, and if this positive charge particle moves in this direction, say if I have one charge particle, a minus charge particle, and this minus charge, this is the direction of my B, then this charge particle, this charge particle is moving in the same direction. The velocity with which the charge particle it moves is the same with respect to B. Over here also, if I have a positive charge particle, and this positive charge, this is the taken direction of our magnetic field, then if it moves in the same direction, that means this is the meaning. That means velocity of the velocity of the charge particle is moving on the same direction. So we have to determine where there will this charge particle experience force or not. In this case, it is very clear that the direction of v, okay, this direction of the velocity vector, as well as the direction of the magnetic field vector are in the same direction, which means that theta in this case is equal to 1. Theta in this case is 0 degree, which means that if you calculate the force, you'll find out that the force will be equal to 0. But making on the one condition, that even though if the magnetic force is 0, but still the particle is moving on the same direction, in the direction of B. Okay, in the direction of B. So from here, this will represent the direction of the velocity vector, and this yellow colored ray will represent the direction of Y magnetic field vector. So in this case, when the particle, okay, according to this description, when the charged particle is moving parallel to the direction of the magnetic field, which means that they are in what? They are in the same direction. So theta in this case will be equal to 1. Theta in that case will be equal to 0 degree. So if theta is equal to 0 degree, if you calculate the direction, if you calculate the magnitude of the force, so if you substitute on that equation, okay, since it is moving, since the charged particle is moving, so V is non-zero. So that is why I have not put V equal to 0. But over here, the angle between V and B is equal to 1. This angle over here, it is equal to 0 degree. So that is why when you put in place of this theta, you put by 1. You put by 0 degree, but we know that sine of 0 will be equal to 0. So over here, this will be VQV into 1 into 0, which gives us that the force is what? That the magnetic force is equal to 0, which means that there will be no magnetic force. Okay? Even if the particle is moving, okay, no doubt that the particle is still in the state of motion, but there will be no magnetic force. That means over here, if if velocity and magnetic field are parallel to each other, still particle is moving. Okay, still that particle is moving. Still that charged particle will be moving, but it will move in the same direction. Still that charged particle will be moving in the same direction of the velocity. Okay? In the same direction of your velocity, okay, v bar. Now, the only possible case when the charged particle experience a magnetic force is only when the charged particle is moving perpendicular to the direction of the magnetic field. In such cases, the angle between that means moving, it is v, okay, and the direction of the magnetic field will be v. That means only for the case when theta is equal to 90 degree, then and only then the the charged particle will experience a magnetic force. So, like for instance over here, suppose if this is the direction of my magnetic field and this is the direction of the velocity with which the charged particle is moving. If I consider a positive charge is moving on this direction, and this will be the direction of my magnetic field represented by that yellow colored ray, then both these V and B are at right angles to each other. Then over here, if you use your right hand from your direction, then you can find out what is the magnitude. Okay, so from here, let us first calculate the magnitude. Magnitude will be given by BQV sine of theta. So what is the angle between V and B? Since V is perpendicular to B, it is obvious that the angle between them is equal to what? It is equal to 90 degree. So over here, if that is equal to 90 degree, then in place of theta, you put by 90 degree. We know that sine of 90 degree is equal to 1. So you'll have BQV into 1. Okay, BQV into 1. So BQV into 1 will be equal to BQV, which means that this force, okay, this force in this case will be what? Will be maximum. So maximum force will be experienced when the direction of the velocity vector and the magnetic field vector are in perpendicular direction with respect to each other. Okay, with respect to each other. So from here, if you have determined this magnitude, then you also have to find what? You also have to find the direction. So how will you find the direction? We can find the direction by using certain rules. We can use the Fleming left hand rule for positive charge, and we can use the Fleming's right hand rule of negative charge. Say like for instance over here, if I take this Fleming's left hand rule, okay, if I take this Fleming's left hand rule in this case, okay, so from here I will take this Fleming's left hand rule and then I will apply over there. Okay, I will apply over there and then see what happens. Okay, what happens. Then over here, when you look at this figure, that means this is my left hand. That means I will try to orient my left hand in such a way that my left hand, okay, I will try to orient my left hand in such a way that this is my positive charge particle. For the positive charge particle, you use what? You use your Fleming's left hand rule. Your Fleming's left hand rule states that you outstretch your fingers in such a way that the thumb, okay, this thumb indicates the direction. The thumb will indicate the direction of your magnetic force. Okay, the thumb will indicate this thumb will indicate the direction of your magnetic force. Okay, this will indicate the direction of your magnetic field, and this will indicate the direction of your velocity. So from here, when you use your Fleming's left hand rule, that means by using the Fleming's left hand rule, making use of those features you have to find. Okay, force, this is the force, this is the direction of the magnetic field, and this is your direction. So from here, when you make use of your right hand, it is very clear that when you rotate this, finger in this way, this will be the direction, that will be the direction in which how you will have to rotate, this is aligned, this is force, this is the direction of my magnetic field, this is the direction of my magnetic field, and this will be the direction of my taken V, or velocity. So this is the velocity, this is the direction, your force. Okay, if you place, that means your force of the magnetic field over here, this force on this positive charge particle will move perpendicular and outwards. So it will be represented by the dot. So it will move outwards. If you are in your paper, if you are doing on a paper, that means it will be out of the page. And if you are looking on your screen, that means this force, this magnetic force, will be perpendicular and out of the screen. Okay, perpendicular and out of the screen. So those are some of the main important emphasis, okay, with regards to what? With regards to application of the Fleming's left hand rule to find out what? To find out the direction. Okay, to find out the direction. So similarly over here, I'll just do the write up. Yeah, I'll just do the write up. So from here, we will discuss certain examples. Okay, the following are the sign convention. So following are some of the conventions. Okay, for representing the magnetic force. Okay, if the magnetic force on a charge is moving inwards, so we will represent by cross. If the magnetic force move outwards and out of the page, that means we will represent by what? We will represent by the dot. Okay, so we will represent by the dot. And over here, we adopt certain rules. Okay, certain rules for the positive charges. Okay, for positive charges, say like protons or alpha particles. Okay, we will make use of what? We will make use of the left hand thumb rule, or Fleming's left hand thumb rule, in which this thumb, okay, the thumb will indicate the force. Then this index finger will indicate what? The magnetic field B, and your central finger will indicate what? Will indicate your velocity. So you have to outstretch all your fingers in this direction. So first you have to stretch your fingers in the direction of your velocity field. Then outstretch your fingers in the direction of the magnetic field. Then the direction in which the thumb points, that will indicate the direction of what? Of your magnetic force. Then also you can use your right hand palm rule for positive charges, which I will discuss in the next section. Over here also for negative charges, okay, for negative charges, like for the case of electrons, okay, for the case of an electrons, we can use your left, you can use the right hand. This is your left hand, and in this case, this is your one. This is our right hand. So you take your right hand, and in such a way that the same convention, the thumb will give you the force, and this forefinger will give you the magnetic field, and this will give you the velocity vector. Then the direction in which the thumb points, that will give you the direction in which the thumb points, that will give you the direction of your magnetic force, okay, magnetic force. So from here, we can also apply the right hand palm rule. For applying this right hand palm rule, that means it is very, very interesting by considering some of the examples, okay. So from here, first of all, when we apply the palm rule, that means over here, if I have this hand and these are my fingers, okay, these are my fingers. So you outstretch your fingers. First of all, you align your fingers in the direction of your velocity vector. Then next, you will curl your fingers, okay, you will curl your fingers in the direction of your magnetic field. Then the direction in which your thumb points, that will give you the direction of your